Hello everyone, welcome to this video. In this video, we are going to learn about NARX using OpenMathAI. So, let's get started. What is NARX? NARX, or Nonlinear AutoRegressive Model with eXogenous inputs, is a supervised machine learning algorithm used for time series prediction and dynamic system modeling. Unlike traditional regression models, which mainly use only the current input values, NARX uses both previous system outputs and previous external input values to predict the current or future output. NARX works by creating delayed values from the input and output data. It uses these previous values to learn the dynamic relationship between the system inputs and outputs. During prediction, NARX receives the recent input values and previous outputs, then uses a learned nonlinear relationship to predict the next output. For multi-step prediction, the predicted output can be fed back into the model to estimate future values. Imagine we want to predict the output of a dynamic industrial system. The system receives a control input, experiences a disturbance input, and operates under different operating conditions. Since the current system output depends not only on the current inputs but also on previous inputs and previous outputs, NARX uses these historical values to accurately predict the next system output. During training, NARX automatically creates delayed input and output values from sequential data. It learns how the current system output depends on previous control inputs, previous disturbance inputs, previous operating conditions, and previous system outputs. Once the model is trained, OpenMathAI uses a learned delayed relationships to predict the system output for new sequential input values without retraining the model. So, let's get started. Open OpenMathAI. In this demonstration, output of a nonlinear dynamic system using the NARX model. Click Create New Project. Enter the project name as Dynamic System Output Prediction. Choose a folder location to save the project, then click Save. To import your dataset, either click Load Example Dataset or browse for dataset to import your own CSV file. Once the dataset is loaded, verify that it contains all columns before proceeding to model training. Scroll down to view the first 10 rows of sample data. Click Continue to Configuration to proceed. Configure the dataset by specifying the input features and output target. There is also a feature called Ignore, which can be used for columns that should not participate in model training. Select the input and output columns manually or use Smart Suggest for automatic recommendations. There is one more feature, Signal Diagnostics. There is a free columns. First one is column. It tells which features on the dataset like inputs and outputs name. Second one is VIF if it tells how much correlation of the features. Third column is status if it's OK, moderate, high, redundant, and constant. Review the selected configuration. Click Proceed to Model Design. Choose a model from the available machine learning models. OpenMathAI recommends suitable models and features based on the dataset. For this demonstration, select the NARX model. View the model overview, pros, cons, and real-world applications. Click Proceed to Training. You will see the selected model. Click Train Models. Review the training configuration, test data split, which determines the percentage of data reserved for testing and validation. Review the model parameters and pre-processing settings. And also the another feature is added that is trained from scratch or continue from use model. If you train this model before you use that option, modify the configuration if required. Click Start Training to begin the training process. After training is complete, review the following performance metrics. R² measures how well the model explains a variation in the output data. Range 0 to 1. MSE, mean squared error, measures the average squared difference between actual and predicted values. RMSE, root mean squared error, the square root of MSE. RMSE is expressed in the same units as the output variable, making it easier to interpret. Engine time, the time required for the generated model engine to execute and produce predictions. Lower engine time indicates faster model execution, which is important for embedded systems and real-time applications. Fit quality, an overall assessment of how well the model fits the dataset. It is generally derived from tricks such as R², RMSE, and residual errors. Model accuracy is commonly estimated using the R-squared value. Example, R-squared equals 0.95 accuracy, almost equal to 95%. Click Fit to Window. You will see 3 types. Fit to Window, comfortable, compact. Then the Clear History. If you click that, it will clear the history before its trained model. Another is Deselect and select all trained model for export. Click View Curves. You will see the diagram of R-squared residuals and residuals diagram. Click Math and Code Preview. View the generated mathematical equation and source code. OpenMathAI provides expression of the data, detailed explanation of the expression, and an implementation code. Return to the result page and click Deploy Status. Click Export Model. Choose the required export format: ANSI, FMU 2.0, FMU 3.0, Verilog RTL, VHDL RTL, Python Bundle, ONNX Hub. You can choose any of these formats and export. You can also download the free trial versions of OpenMathAI and Twin Simulate. Thank you. Stay tuned for more OpenMathAI demonstration.